not a claim that quantum computing is breaking modern encryption today. This is not a claim that this Nature paper reveals a hidden exploit. And this is not a speculative sci-fi discussion about distant future. The paper we're discussing is a capability review. It surveys how artificial intelligence is being used to make quantum systems more usable, more scalable, and more automated. From a research perspective, that's exciting. From a vendor perspective, it's commercially necessary, but from a security and compliance perspective, that capability acceleration is potential breach of duty machine. Whenever a technology reduces human bottlenecks, automates control over physical systems, concentrates knowledge into machine-learned artifacts, or lowers the barrier to sophisticated operations, it creates new attack surfaces and new legal obligations. That's the lens we're going to apply to all the episodes of the series to come. I'm Nupur Mitra, a legal and governance risk translator for AI systems. This is the quantum AI threat almost nobody's talking about. Follow the AI Law, my channel, for daily breakdowns starting January 12th, Monday 2026. So the central framing of this task is simple. The security risk is not quantum computing itself. The security risk is AI-enabled operationalization of quantum systems. Quantum hardware in a lab is relatively inert from a security standpoint. Quantum hardware controlled by ML-driven pipelines, exposed via cloud platforms, trained on sensitive telemetry, and developed through international collaboration is a very different thing. That shift from experimental physics to automated cyber-physical systems is exactly what this paper is describing. Our job today is to understand what assets they emerge when AI is embedded into quantum workflows, how those assets can be attacked or misused, what controls vendors must implement to remain secure, compliant, and credible. A common mistake is to think quantum is in production yet, so security can wait. That assumption is already false for 3 reasons. AI collapses timelines. AI doesn't just improve performance, it compresses development cycles. Tasks that used to take months of expert manual tuning now happen automatically and repeatedly. Security timelines track automation, not scientific milestones. 2. Data and models are valuable before hardware scales. You don't need a million-qubit machine to leak proprietary device, fingerprints, control heuristics, or decoder strategies. Those assets are valuable today to competitors, nation-state labs, and supply chain adversaries. And 3. Regulators don't wait for commercialization. Export controls, cybersecurity regulations, and contractual obligations apply during R&D, not after product launch. Many organizations discover this only after exposure occurs. So this is not a future quantum problem. It is a current AI plus data governance plus supply chain problem. This opening slide has 3 jobs. Define the scope. We are focusing on vendors and developers, not abstract research. Anchor the threat model. Capability acceleration creates risk. Set the mental model. Think cyber-physical systems, not just code. Everything that follows, threat actors, attack surfaces, compliance checklists, flows from this foundation. If you imagine a triangle at the center of the slide, the 3 corners are capability acceleration. AI reduces friction in calibration, compilation, decoding, and control. ML in the loop control. Machine learning systems don't just advise, they act on hardware. Sensitive and controlled data. Telemetry, device fingerprints, model weights, and control parameters are all high-value assets. Security risk emerges not from any one corner alone, but from their interaction. Remove AI and systems are slow but understandable. Remove sensitive data and models are less powerful. Remove automation and humans remain the gatekeepers. This paper is explicitly about bringing all of these 3 together. One of the most important things to understand here is that research papers do not use security language, even when they describe security relevant capabilities. For example, when the paper talks about learning device characteristics otherwise inaccessible to into experiments. A security professional hears latent information extraction and reverse engineering. When it discusses optimizing control voltages using ML, a security professional hears automated control plane decision making. When it describes AI decoders implemented on FPGAs, a security professional hears firmware integrity and silent correctness risk. So this paper isn't wrong, it's just speaking a different dialect. Our task as vendors is to translate capability into responsibility. This threat model applies most strongly to vendors and developers, not purely academic labs. Why? Because vendors store large volumes of telemetry and customer data, deploy ML models repeatedly and automatically, expose systems through APIs or cloud platforms, operate across borders, and are contractually accountable to customers. So in other words, vendors turn capability into infrastructure, and infrastructure is what attackers, regulators, and litigators care about. Another clarification. When we say security, we're not only talking about hacking, breaches, or malware. We're talking about 4 overlapping risk categories: confidentiality, integrity, availability, and safety and correctness. Confidentiality, trade secrets, customer circuits, device telemetry. Integrity, calibration correctness, decoder accuracy, model authenticity. Availability, uptime of scarce quantum resources, prevention of subtle denial of service attacks. Safety and correctness, preventing silent errors, ensuring experimental and customer results are trustworthy. So for quantum vendors, correctness is a security property. If results can be subtly biased or degraded without detection, trust collapses. This is just an introduction here today. We'll be detailing it later in the series. Even on this first slide, it's important to flag that legal exposure is inseparable from technical risk. This includes export controls and deemed export rules, trade secret law, contract and liability exposure, emerging cybersecurity regulations for digital products. Later slides will unpack these in detail. For now, understand this. Security failures in quantum systems are rarely just technical. They tend to escalate quickly into regulatory reporting obligations, customer disclosures, and reputational damage. So, having established the framing, here's how the rest of the presentation unfolds. We'll identify the crown jewels that emerge in AI for quantum systems. We'll map realistic threat actors to those assets. We'll walk through concrete threat scenarios, each directly derived from capabilities discussed in this paper. We'll then translate those threats into a practical compliance checklist that engineering, security, and legal teams can actually implement. Finally, in this series, we'll discuss how to operationalize this without slowing innovation. The goal is not fear. The goal is resilience with credibility. So this one sentence would frame everything that follows in the series. In quantum technology, the moment AI enters the control loop, security stops being optional research hygiene and becomes operational risk management. So with that framing in mind, let's move ahead and define exactly what assets are at stake.